Welcome to the Chapter 10 review for AP Statistics. This one is about comparing two populations. This one is actually a bit shorter than the previous ones, and it also builds on what we learned before. It's very similar to what we learned before, so it's going to be a shorter video. I'm not going to go into the examples in depth. I will show you examples, and you can pause the video and write the full response yourselves, but I won't go through how to write the full response because that's just very similar to what we did before. So if you do want to know how to write that, refer back to the chapter 8 and 9 videos for confidence intervals and significance test, respectively. All right, let's get into the actual statistics. So our first section is 10.1, comparing two proportions. We're going to also talk about means in 10.2, sorry. Now, for proportions, before we talk about conditions and everything, which we usually do, we're going to have to talk about the sampling distribution. When we only had one population, it was pretty simple. We knew the different characteristics of the sampling distribution. But when you have two populations, you need to know the shape, center, and spread of those. Let's start with the shape. The shape is going to be approximately normal if the normal condition is met. And I'll tell you about the normal condition a bit later. But if that condition is met, then the shape of the sampling distribution would be approximately normal. The center is going to be the mean. So it's going to be P1 minus P2. And honestly, order doesn't matter, but just be sure to be consistent throughout the entire thing. P1 minus P2 is the difference of the two population proportions, and that's going to be the mean of the sampling distribution. And the standard deviation for spread, it's going to be the square root of P1 times 1 minus P1 over N1 plus P2 times 1 minus P2 over N2. Pretty similar to the standard deviations for just one population each, but just combine it together. You square the standard deviations, add them together, square the entire thing. Pretty similar to actually what we talked about a few chapters earlier. When combining two samples, you would do the square root of the sum of the squares of the standard deviations, which is basically what we're doing here. All right, now that we covered that, we can move on to the different conditions. As with just one sample, it's random condition, 10% condition, and normal condition. Random condition basically says that the data should come from two independent random samples. Or it could come from two groups in a randomized experiment. If it's an experiment, you can use that as your criteria. 10% is, as usual, for each sample, the sample size has to be less than or equal to 1/10 of the population size. For each one, you have to do it for both. However, if it is an experiment, you can just write NA next to the 10% condition, just like NA, or leave it blank. I would prefer to write NA because it shows that you acknowledge that you don't need it instead of just the reader might assume you forgot about it instead of just knowing that you don't need to write it. And finally, the normal condition, the one we've all been waiting for, so we can go back to this, it's going to be NP hat is greater than or equal to 10, and 1 minus p hat is greater than or equal to 10. But that's only for one sample. For two, you're going to need n1 p1 and n2 p hat 2 is greater than or equal to 10, and 2 1 minus p hat 2 is greater than or equal to 10. And if all four of these are true, then the shape of the sampling distribution is going to be approximately normal. And we'll be ready to do confidence intervals and significance tests on these two proportions. So how are we going to do a confidence interval? It's going to be a two-sample z interval. We've done one sample z interval for proportions. Get ready for two-sample z interval. The formula for this, well, we know the mean is p hat 1 minus p hat 2. I know we said it was P1 minus P2 before, but that's when we knew the population proportions. Now we don't. All we have are the statistics, or the sample proportions. So this has to be our mean. Our test statistic, Z, so we're going to use the critical value Z star for a C% confidence interval. I hope you know how to do that from chapter 8. And finally, our margin of error, which includes the critical value and the standard error. The standard error is going to be square root of p hat 1 times 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. Very similar to the standard deviation of the sampling distribution, but with hats instead of not without hats. Or sorry, hats instead of without hats. Yeah. Putting it together, you have the mean plus or minus z star times this standard error. Just plug that in right here. That's how to do it manually, and you do need to know this. It's best if you write this down in your work while using your calculator for actually calculating the values. But to calculate the values, you would just use this function on your calculator. You go to statistics, confidence intervals, which is part of tests, and you go to not two sample z interval, but two prop z interval. We're never going to use two sample z interval. Samples don't go with z intervals. It's always going to be two prop because we're dealing with proportions. So just be wary of that. Even though we call it a two sample z interval for proportions, on our calculator, it's not two sample z interval, it's two prop z interval. Okay, with that out of the way, we just plug in the successes and n1 for the first population and successes in n2 for the second population. And then our C level, and it does it for us. But still show this in your work. Moving on to significance tests. We use a two sample z-test. Again, on your calculator, it's going to be two prop z-test, but we're not there yet. The formula is going to be z is our test statistic. It's going to be p hat 1 minus p hat 2, and then it's usually a minus 0, because 0 is our null hypothesis saying that p hat 1 minus p hat 2 is equal to 0. That's our null hypothesis. Or actually, it's just p 1 minus p2 is equal to 0, because null hypothesis, we talk about the actual parameter, not the statistic. So another way you can write this is p hat 1 minus p hat 2 minus p1 minus p2. Most of the time, that's going to be equal to 0 because of your null hypothesis. And since it's 0, you can just ignore it completely. But best form to write it out to know where it comes from. So that's the numerator. In the denominator, we have the standard deviation. But there's a little variability. If it was just the standard error, p hat 1 times 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. That is what we did for confidence intervals, but there's a little caveat. We can't do that for tests, for the significance test. Instead of p hat 1 and p hat 2, we're going to be doing something called p hat c times 1 minus p hat c. It just c's everywhere. And what is p hat c? It's something we call the pooled or combined sample proportion. The formula for p hat c is basically going to be the number of successes in the first plus the number of successes in the second divided by the sample size of the first plus the sample sizes of the second. So it's not just the average of the two proportions. It's a bit different. It would be this formula. Make sure you separate into successes and sample size. Add up the successes first before dividing by the sample size. There you go. That is going to be your formula for Z. Once you get Z, you're going to use normal CDF, like we did with significance tests in chapter 9. Plug in your Z value and get the P value, which is the area resulting from normal CDF. All right. With that out of the way, let's do an example, shall we? And this example is actually going to be about significance tests. Now, I could also do an example about confidence intervals, but that would just be rehashing the same things. So for means, I'm going to be doing an example about confidence intervals rather than significance tests. So one of each, basically. This example we did do, it's our teenage hearing loss, basically. Our teenagers losing their hearing at an increased rate. It's talking about two studies, one a while back, 15% of the 3,000 teenagers showed some hearing loss. Then later, 19.5% showed some hearing loss in a study of 1,800 students. And part A, do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Well, convincing evidence, that screams significance test. What we can do here is, well, what would be the successes? I guess to sort of neaten it out, sample or population one. Let's go with pop one and pop two as our table. You wouldn't actually do this in your response. I'm just showing you like a nice way to organize things. The sample size is going to be 3,000 for the first population, 1,800 for the second. Now, the proportion is going to be 0.15 and 0.195. Now, what does that make the X values? X meaning the number of successes. In this case, hearing loss isn't really a success you would celebrate, but that's the statistics terminology. You would just multiply the proportion by the sample size. So 0.15 times 3,000 is 450, and 0.195 times 1,800 is actually going to be smaller, so it looks odd, but then that's when you have to remember that the sample size is much smaller, so it kind of makes sense. With that, we do have enough information to come up with our statistics test, or significance test. We could use the formula we learned, and you can do that. You should do that when you're writing your response. But since it's just a brief example, I'm going to use the calculator, 2 prob z test, not 2 sample z test. I have to reiterate that. The number of successes 1 is 450, and 1 is 3,000. Number of successes 2 is 351, and N2 is 1,800. Now, what's our alternative hypothesis going to be? Now, you would already have written this down in your response. We didn't do that here because we're not writing a full response. I'm just showing you the process of what you should do. What's the alternate hypothesis going to be? Well, the null hypothesis is that P1 minus P2 is equal to 0, right? Because there's no difference. But the alternate hypothesis says, is it an increased rate? We're suspecting that the hearing loss is increasing. So P1 minus P2 is actually less than 0. Because P1 is the old study, P2 is the new, so old minus new should be less than 0 if the new is greater than the old. You can do some algebra, figure it out, but that's going to be our alternate hypothesis. So it's basically going to be P1 is less than P2. Plug it in, you get a bunch of information. The important stuff are Z is negative 4.048, and your p-value is going to be 0.0000258, for example. Now, is that statistically significant? It doesn't tell us what the alpha level is. We assume it's 0.05, but anyway, in most of your scenarios, that is going to be a statistically significant p-value. It's actually close to 0. Some calculators might give you a p-value of 0 if you plug that. Now, you write your concluding statement. Because p is equal to blah, 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 which is less than 0.05, we reject the null hypothesis, and there is convincing evidence that the hearing loss has increased. And you have to write in context, basically saying from the 1988 to 1994 to 2005 to 2006 and so on. Okay, that's part A. Part B. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, which they are, can we blame iPods for the increased hearing loss in teenagers? Sure, seems like a factor, right? But statistically speaking, can we? The answer is no, which you might have guessed because of the fact that they're asking that question. But the reasoning is also important. And that's because, well, can we blame iPods? That means we're saying iPods caused the increased hearing loss, caused causation. You need an experiment to prove causation. This is not an experiment, it's a study, meaning we cannot say that it's iPods. We need to have an experiment to prove that it's iPods that caused the increased hearing loss. Another thing I didn't do here, conditions, always do that in your written response. I'm not doing it here because we already know the conditions are going to be met, but you can do that on your own to test it out. Okay, so moving on to means, we're finally at 10.2, means. Same kind of information. Sampling distribution has a shape that's approximately normal if the condition is met. The center is going to be the mean. This time, actually, as you might imagine, the mean is going to be mu1 minus mu2 instead of p1 minus p2 because it's means and not proportions. And we've got standard deviation. This one is going to be similar to proportions, actually. It's going to be square root of the first standard deviation squared plus the second standard deviation squared. However, there's a formula for the standard deviation that we use, and that's it's equal to the actual standard deviation divided by the square root of n. So when you square that, you get the first standard deviation squared over n1 plus the second standard deviation squared over n2. That's your standard deviation for the sampling distribution. I just X this out because that's the old formula that we used to use. This is two means, meaning we use this new formula. All right. I'm just rushing through the means because it's very similar information to the proportions. Conditions, random condition, 10% condition, and normal condition. Random basically is, it has to be an independent random samples of size n1 from population 1, n2 from population 2, or like with proportions, it can be two groups of size n1 and n2 in a randomized experiment. 10%, same thing. The population of each has to be at least 10 times the sample size of each. And if it's an experiment, you don't need 10%, you just write n. Normal is where it gets fun. You might remember this from the last few chapters, but there's a few things we have to do for normal. First, check if the population is normal. If it is, then you're going to be having a normal condition is met. If it's not, if you don't know the shape, you have to see if the sample size is greater than or equal to 30. That's called the central limit theorem. So n1 is greater than or equal to 30, and 2 is greater than or equal to 30. That means the normal condition is met. If that's not true, you have to see if the graph of the data, of each data, is basically approximately normal. And what that means is no strong skewness, few outliers, if any. And what you have to do for that, you have to create a box plot and a normal probability plot for each one, draw them there, and you're good to go. This is only if the sample size is less than 30. Okay, moving on, degrees of freedom. We talked about this before. Degrees of freedom is just going to be n minus 1, but that was back then. There is a different thing here, and there's actually a much, much, much more complicated formula for degrees of freedom in this unit because there's two samples. We're not going to be talking about that. You could use technology to calculate degrees of freedom, or what's probably easier for you is to use the conservative approach that you take the smaller sample size, let's say it's n1 and n2, let's say n1 smaller than n2, degrees of freedom is going to be the smaller one minus 1. Because it's conservative because degrees of freedom is less than it would be if you use the accurate value. And if it's less, that means you have a wider confidence interval or a lower p-value, which means it's going to be more, I wouldn't say it's basically more conservative. Let's just leave it at that. All right. Now that we talked about that, we can finally get into both confidence intervals and significance tests. Starting with confidence interval is going to be a two-sample T interval. Now, what is the formula for that? Well, you need the mean, which is x bar 1 minus x bar 2. You need the critical value, that's going to be T star. And again, how do you find T star? You basically do inverse T of your area, and you're going to get the T star value. And you need the standard error, which is going to be, as we kind of discussed, S1 squared over n1 plus s2 squared over n2. We're using s instead of sigma because it's a sample, it's a statistic, not a parameter. Putting it all together like we do with proportions, it's going to be the mean plus or minus t star, and then you just do that times this right here. The t star times the standard deviation is a standard error is going to give you the margin of error. Pretty normal stuff here, no pun intended. Moving on to significance tests. This time we don't need anything like pooled or combined sample proportions. We did that with proportions. We don't need anything like that for means. It's just going to be a straight t statistic where it's x bar 1 minus x bar 2 minus mu1 minus mu2. Same thing like we did with proportions. This is usually going to be 0, meaning we can cancel that out entirely. But for completeness sake, let's leave it as 0 because it's usually going to be that. Over square root of s1 squared over n1 plus s2 squared over n2. As you might expect, that's the t statistic. We use that for the t-test. You find this value, you do t-CDF, not normal CDF, t-CDF, plug that value in, and whatever area you get, that's going to be your p-value. And if it's less than alpha value, then it's statistically significant. If it's not, then it's not. Just like with one sample, but it's just a bit more complicated of a formula. Okay. Using your calculator, you can do 2 sample t-interval and 2 sample t-test respectively to get the same result, but you should definitely show your work in your response to ensure that you receive all the credit you deserve. Okay, time for an example. We also talked about this one. It's about chocolate chips. Basically, we want to see if generic chocolate chip brands, basically Great Value in this case, versus the name brand chocolate chips, Chips Ahoy, we want to see which one has more chocolate chips on average. In other words, or more specifically, actually, we want to see if Chips Ahoy has greater chocolate chips than Great Value, because we suspect that name brand chocolate chips are better than generic chocolate chips. This one's a confidence interval, like I promised. So in this case, you would start off by checking the conditions, random 10% normal. They should be all met. I'm not going to go through that. Again, this is just a brief example, not an in-depth one. You definitely should state the hypotheses, check the conditions, everything like that. But this is data, so you have to enter that into your lists. Once you do that, you're going to do, you could calculate the t statistic by hand, or the t star value. You're going to need to calculate that first. You could use inverse t and everything. You could calculate the standard error. You could do all that. I'm just going to use my calculator for this one because, like I said, it's a brief example. So you're going to do statistics, and you're going to go into tests. And in that, you're going to go into 2 sample t interval, not 2 sample z interval. We never use that under any circumstance. You go to data, you enter the 2 lists in. And this one is actually interesting. So obviously you choose sea level, it's 0.99 in this case, but there's something called pooled. It's always going to be no, never do pooled. We don't even know what it does, but just don't do pooled. Click enter, you're going to get a bunch of information, important information, the margin of error, for example, degrees of freedom if you want. Mainly what you want is the lower and upper bounds. You're going to get negative 4.814, comma 2.814. That's your lower and upper bounds. That's the 99% confidence interval that you constructed. And then you have to interpret it. I'm not going to do that here because it's just a brief example, but you say we are 99% confident that the interval from negative 4.814 to 2.814 captures the actual mean difference, blah, 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 and so on. Interpret in context. Part B says, does your interval provide convincing evidence that there is a difference in the mean number of chocolate chips? Well, we briefly talked about stuff like this in chapter 8 with confidence intervals, but basically, is there a difference? Well, if there's not a difference, that means zero is the difference. Is that in the interval? Yes, zero is in the interval, meaning there's not convincing evidence that there is a difference in the mean number of chocolate chips. Because since zero is in the interval, it's a very plausible value, um, meaning that it's plausible that there's no difference. So there is no convincing evidence that there is a difference. So B just says no, and then you have to explain why and everything. That's actually it for the video because that's basically all we learned. It was a very short chapter, so this video is shorter than the rest. So we talked about comparing two populations with proportions and means, talking about confidence intervals and significance tests. That was chapter 10. Good luck on the test. Bye.